Section 14.2, we're going to be looking at, the name of a gentleman that we've seen before. Do you remember seeing this name before? Euler?
Yeah.
Euler, yeah. We saw it with Euler diagrams. It was the section in chapter 3 where we're looking at truth tables and things like that, and there was a section 3.5, I think it was. It was all about Euler diagrams. So today we're going to be taking a look at Euler circuits. So mathematicians do not typically work in a bubble. Sometimes they dabble across different branches of mathematics, and Euler would be someone who did that. So we've talked about what paths and circuits are, but we're getting this sort of adjective at the beginning of it that says Euler paths and Euler circuits. So there's a distinguishing feature. An Euler path is a path. Remember, path means you can't do what? Repeat edges. Okay, so we've got something you can't repeat edges. But if it's an Euler path, it also uses every edge in the graph. Okay, so it uses every edge and you can't repeat it. Write that down if that's helpful to you. An Euler path uses every edge and repeats none. Okay? This would be the idea of what you would want to do if you were trying to organize your day to save your money on gas, right? I don't want to go to Walmart and then go over to Walls, and then go from Walls back to McDonald's by the Walmart. I don't want to keep doing this back and forth business if I'm trying to conserve my gas. Okay, Euler path. Euler circuit, however, is a circuit that uses every edge exactly once. So it takes what we know about paths, it takes what we know about circuits, and it says, I have to cross everything. Right? I got to check off everything on the to-do list. I don't just get to decide that today I'm not going to do this errand. I need to do it as well. Okay? So I accomplish everything without repeating anything. That's really what I'm doing. And in a circuit situation, I'm starting and ending at the same place. So we're going to take a look at an example. You've got this diagram. And it's listing, there's 3 of them, 2 of them on the screen. I'll drag this over to the other screen if it's not already there when we get to the third one. It wants to know which of the following are Euler circuits, specifically circuits. It does not ask us to find paths. It does not ask us to find walks, any of those kind of things, just specifically circuits. And it says for any that are not, explain why not. And we're going to try to be as descriptive of the ways that they fail as we can, because there's no guarantees that what I'm showing you when we write down one piece of it failing is the same way that something else is going to fail. So I want to make sure you see how to think through all the ways that something can fail. It sounds like a bad thing, but for what we're doing here, it's okay. All right, so the first one is A to B to E to D to A. So you're welcome to use colors. I will do that as well. We'll start with orange. So it says from A to B, and then B to E, and E to D, and D to A. That's what I have. Is it an Euler circuit? No. Is it a circuit?
Yeah.
It is a circuit. So at least it fits sort of part of the description. So it is a circuit. I'm just going to mark that not because I was asked, but because I don't want us to sort of fail to recognize what we do have. It is a circuit, but not an Euler circuit. Why not? Yeah, it doesn't use every edge. I'm going to say it misses some edges. So it's failing. We'll use another color. How about yellow? All right, A to B, B to C. Man, I failed fast, didn't I? It's not possible. Why? There's no edge that connects B to C. So this fails badly. Like it's not even a walk, right? I can't even do it unless I go on the grass. And there's probably a sign that says keep off grass, right? Don't do that. Right, so this one fails. And so let's actually write that down. So it's not a walk. Because B to C is not an edge. Let's assume for the moment that it were, and let's just keep going and see what else we have as potential problems. Let's say that there's actually an edge connecting B to C. So if there were, I'd go from A to B. I'll keep coloring in yellow as though it matters. A B to C. C to D, again, also not an edge, right? So we could find that, sort of categorize that in the same thing. So neither is C to D. Is it C to D? Yeah. Let's keep going. So C to D. D to E. That one was an edge. And then E to G. Also an edge. So what else does this fail to do? Okay, doesn't go back to the starting point. Okay. So it's also not starting and ending at the same place. Anything else?
It doesn't use all the vertices.
And it isn't even so much vertices, although we'll find another situation where vertices matter. It's the edges, right? So that it's not ending at the same point or same vertex. And it misses edges. Yeah, so it's just all the way around a bad situation, right? We have so many things that it fails for. But these are all things that you should be looking for, right? It needs to pass all those criterion. So you don't necessarily have to find all those criterion unless it's like one of those where it's a multiple choice question where it says, you know, why is this not work? And then it might be one of those choices. That's happened before in some of your work. Once it doesn't work, it's definitely just not going to work. And sometimes those questions are just, is it not? It's a yes or a no, right? Sometimes there's questions like that. Here's your third one. Let's see. We're going from, I already used that color, even though I'm on a different screen. Let's use blue. So I'm going from A to B, B to E, E to F, F to G, G to E, E to D, D to A to E, E to C, and C to A. Did it work?
Yeah.
Wow, there's a lot of movement, yeah. This one works. I would like to point out that something interesting failed. It's not something we were checking, but failed. That's an okay failure in terms of things you might have thought you were checking. Did you notice that you visited A multiple times? Yeah, and that's okay. Euler circuit doesn't have a contingency problem with that. Like there's no problem with it visiting A twice. You can do that. We're going to see something in section 14.3 where we can't visit the vertices multiple times. But with an Euler circuit, we can. So we're good to go on this. Crosses all of our edges once and not more than once. All right, Euler's theorem then. Euler's theorem says the following. Well, you might have thought, well, that was really nice, but what if they asked me to create one of those suckers because that was really messy? How do I create one, right? Or how could I decide if even one can be created? That's what Euler's theorem is about. So Euler's theorem says, suppose we have a connected graph. So we must have a connected graph for this to even make sense. If the graph has an Euler circuit, then each vertex of the graph has an even degree. Notice what it doesn't say. It doesn't say if it has an odd degree, what happens, right? It doesn't say anything about what happens for odd degree. So it's not saying if it's an odd degree, it's not going to work. That is not what it says. Now, the second statement is the reverse of it. It says if it's an even degrees on all of the all vertices, then we do have an Euler circuit. So it doesn't say what happens with odds. Odds are sort of left out there a little bit, saying sometimes they work and sometimes they don't. But if you have them even, it's going to work. That's what this is saying. Which means if you were asked to find one, you would be able to find one if you manipulated it carefully, or maybe enough times. So let's take a look at one. It says use Euler's theorem to decide whether the graph has an Euler circuit. What are we going to be checking for? Degrees. So what can you tell me about the degrees? They're not all even. Some of them at least are odd. One of them is even, right? E has even degree. But we can't talk about Euler's theorem and make sure that we have an Euler circuit based on Euler's theorem because I don't have all of the even degrees. So right now, we have to simply say that there's no guarantee of an Euler circuit. In fact, one doesn't exist here because, and I'll list which ones are, A, B, C, and D all have odd degree. So we're just checking degrees to make that decision. Let's take a look at another one. This one again says use Euler's theorem to determine whether the graph has an Euler circuit, much like the last description. But then it has the additional piece at the end that says, then determine whether the graph has a circuit that visits each vertex exactly once, except to return to the starting vertex. If so, write down the circuit. And what we're going to find in many of these problems is that they're going to say something like this. There may be more than one correct answer. So when it says there may be more than one correct answer, that typically means that you're going to be looking at a multiple choice options where you have to pick the ones that work versus the ones that don't. Okay? So taking a look at this one, first Euler's theorem. Let's just write the degrees on everything first. Okay? So let's start with G in the top left-hand corner, like a bow tie. What is the degree on G? 2 over to J, 2 down to K, in the middle to I, and over on the H, 2. Does it have an Euler circuit? Yes. Why? All even degrees. All even degrees. It has an Euler circuit. So yeah, we get that part. So we'll say yes. Euler circuit. That's terrible language. That is not good English, but I'm abbreviating. Yes, Euler circuit, because all the degrees are even. All right, now let's think about the other question it asks. So that's sort of question number 1. Is there a way to create a circuit that will visit each vertex exactly one time before it returns to wherever it begins? No. How come, Gabe?
Because it's going to have to cross over that I at least twice.
The I in the middle, whether I start at I or whether it's just in the middle of what I'm doing, I'm going to have to cross through there twice. Why?
Because there's no other way to get to from G to J. You have no other way to get there but to go through I.
Right. And I've got 4 that are all meeting there, right? So the only way that this would actually work is if I would only have 2 at each of the points. If they all had 2, one way in, one way out, right? One-way road kind of thing, then we'd be good to go. But I don't have that. I have a degree of 4 in the middle, which means I have to be able to go in and out twice, or I'm not going to achieve crossing over every path or every edge. Yeah, so this is not going to work. Very good work. So this is a no. And I'll say it much like what you had said. We will cross through I twice. And technically even 3 times we would hit I if we started it and did it I, right? We'd actually have it 3 times. Okay. Time. Cut edge. All right, a cut edge in a graph is an edge which, if we remove the edge, it will disconnect a component of the graph. So its removal, the removal of a cut edge, actually creates a disconnected graph. And I'm going to draw an example and a non-example. Okay, so we take a look at the first graph I drew. Kind of sprawls out, right? There are edges, in fact there's more than one edge, that if I cut through it, imagine it's string holding it, I would actually break the graph into pieces. Okay? Can you tell me one of the edges that I could cut through that would do that?
BE.
Yeah, BE is probably the most obvious looking one. There are others. So if I were to cut through BE, I would break the graph into two pieces. I'd have the piece at the top, I'd have the piece at the bottom. That's one of the cut edges. Can you see any other cut edges? Again, you only cut one edge at a time. So, Jonathan?
D and E.
D and E. D and E would also cut the graph into two pieces. Okay? A and B, you're right. Not necessarily an obvious choice either. The piece that it disconnects is just a vertice, right? A vertex. But it's still a vertex. It's still part of the graph that's no longer connected to the rest of it, which therefore also means C and B would be that, E and F would be that, or D and G. Like every edge in this graph is a cut edge, isn't it? Now that doesn't happen with the second graph. Imagine cutting any edge of the second graph. A single edge cut on the second graph does not disconnect anything. I can still get from example A, the one that I've marked, from A to D. I just have to go around.
So if the graph has a Euler circuit, does that mean that doesn't have any cut edges?
If a graph has an Euler circuit,
Yeah.
because you have to be able to end back at the same spot without repeating.
so I believe that's true. That might not be a necessary, or it may not be a necessary condition, but it might be a sufficient condition. So Euler graphs or graphs with Euler circuits would have that feature. Yes, you're correct. Yeah. All right, so we're going to look at a graph specifically here, and we're going to identify the cut edges. Now, not all the edges are cut edges. I gave you an example where one of them, all of them are, and on one of them, none of them are. Well, there's some in-between things. What are some cut edges, or what are all the cut edges in the graph that's given here on number 4? EF, CF, and FG. These are the cut edges. I'll write them in segment notation. I can't remember how your book writes them, but we'll go with that. These are the cut edges. Okay, so here's where we're going to stop today. Not here, just a second. We're going to write down the next screen, and then we'll actually do it so that we've got this all written in our notes, and we'll pick up there next time. This is called Fleury's algorithm. It's a good name, right? Fleury. Fleury's algorithm talks about finding, which one is it? The Euler circuits for our graphs. So it tells us we start at any vertex and we go along any edge. It's very arbitrary. Any vertex, any edge, you pick, to any other vertex. And as you do so, you remove the edge that you traversed from the graph. So as soon as you cross, that plank on the bridge, the plank falls down underneath you, right? It's like Shrek. How are you going to get out of the castle? Ride the dragon. I don't know how else you're going to get out, right? Okay, so every time you cross the path burns up behind you, falls down behind you, it disappears. And then in the revised graph, the graph that you got on number 2, you repeat that step, but you do not cross and remove any cut edge unless you have no other choice. And you repeat step 2 until you've used up all the edges and returned to the starting vertex. This process allows you to find an Euler circuit. So as soon as you've jotted all that down, we'll push pause. I will change the due date on the homework. I strongly encourage you to start it, because section 1 that we just finished is the longest section, okay? At least do everything from 14.1. You know how the numbers are coded, right? 14.1. If you don't want to start or do the 14.2 and you want to put that on hold, you'll have the weekend still to do that. But you will have 2 assignments that will be due next Tuesday when you come to class, all right? From 14.1 and 2 is today, and what we finish next time, and 3 and 4, which we'll do next time.